everyone. This is going to be your first video where I'm going to talk to you a little bit about what are called higher order derivatives, specifically the idea of writing something called a second derivative. So that's going to be my title, higher order derivatives. Ordinal numbers are just numbers that let us put things in place, first, second, third, fourth, fifth. For right now, when we have taken a function and I have said take the derivative, okay, which we've all been able to do pretty easily. What I didn't clarify is that that derivative was called actually the first derivative. Okay. When we take the derivative, there are actually multiple derivatives you could take. And so the initial derivative, or the one you take first, is your first derivative. Okay. If I then want to take the derivative of the derivative, the notation I would use would be f double prime. And believe it or not, yep, that's the second derivative. Oops, that's not how you spell derivative. Okay. Now, you can't get a second derivative without having a first derivative. You can't kind of jump to the second derivative. But if I do have a first derivative, just toss this on the next page. Nice and big. Okay. If that's in fact my first derivative, my second derivative would be 6x minus 6. If you want to go further, you can. The third derivative, triple prime, would be 6, just 6. And then fourth, we don't actually use primes. Sometimes I've seen it with a Roman numeral, and I've also just seen it with a 4. In this case, we would hit a 0. And then every other derivative after that, once you hit 0, the derivative of 0 is 0, and you can't go any further. So some functions, polynomial functions, eventually run out of derivatives. The higher the degree of the original function, the more derivatives you can get. We're going to be mostly focused on our second derivative, even though there are applications for other derivatives. First derivative and second derivative are the most common. One of the most common second derivative applications is the idea of acceleration. For people who took physics, velocity is change in position. So it is a derivative for position. It's a first derivative measurement. When we measure how velocity is changing, that is called acceleration. That is a second derivative. Any function can have multiple derivatives. Some functions ultimately will hit 0. Some functions will never hit 0. And if you're thinking like, well, how could you not hit 0 with multiple derivatives? Here's a good example. Let's talk about the square root of x. or x to the 1/2. My first derivative would be 1/2 x to the negative 1/2. My second derivative, I would take the 1/2 times a negative 1/2 x. So I get something like negative 1/4 x to the negative 3/2. If I wanted to go further, I could do the power rule again and get something like 3/8 x to the negative 5/2, and so on. So rational exponents, fraction exponents, we're never going to run out of derivatives. Negative exponents will never run out of derivatives. We can take derivative after derivative after derivative almost infinitely for those. So, it's really not learning anything new. It's just the idea, the concept that I could ask you to find a second derivative, basically take a derivative, and then take the derivative of that derivative. There's no new rules for second derivatives in terms of how to generate them. The same rules get used. If you have a product, you have to use product rule. If you have a quotient, you have to use quotient rule. And if you have something raised to a power, a quantity to a power, you would have to do a chain rule. If the directions say find f double prime of x, you'll be responsible to know that that means the second derivative. And like I said, if I have something like that that requires a little bit of chain rule to take the first derivative, I'm guessing most of you would be able to do that. Then there's a likely chance we're going to continue to need chain rule for our second derivative. Oftentimes when we're going from a first derivative to a second derivative, we may want to simplify first. In this case, there's not a lot of simplifying to simplify, not fly, simplify. There's not a lot of simplifying that can happen, but this 4 and that 2 could make the product of 8. Once I have f prime simplified, I can go right into f double prime. Still using chain rule. Then we get something like that. Once again, might want to clean that up a little bit. A lot of multiplications. I think that's 24 times 2 is 48. 2x minus 5 quantity squared. And that would be f double prime. So chain rule problems, you can end up doing chain rules. Quotient rule problems, you can end up doing more quotient rules. Product rule problems, you can end up doing more product rules. Product rule problems are probably the hardest because essentially when you have one product rule problem and you take a derivative, you make 2 new product rule problems. So it gets big really fast. I just don't stick students in a situation where you have to do multiple derivatives with product rule. Quotient rule doesn't bother, or chain rule doesn't bother me, and actually quotient rule is not too bad. I want to do like at least one specific kind of quotient rule. So let's take a look at that. Let's say this is our quotient function, a really basic rational function. If you want, go ahead and pause this and see if you can write the derivative using quotient rule. I know you didn't pause. So, nothing too fantastic happening here. But the fun thing that happens with this kind of quotient, specifically a regular x expression over a regular x expression, is it simplifies in a really nice way. If I distribute through that 4, I get 4x plus 12. If I distribute through the 1 and the negative, that negative 4x is going to come out, which is going to cancel out my positive 4x. I'm also going to get a plus 1. Oh, I did. Look at me. It's a horrible what a horrible denominator. And so my first derivative, in this case, in the quotient rule, actually is kind of nice. It simplifies pretty well. Now, if we wanted to do another quotient rule with this, we could absolutely do it. It would require a little chain rule in the middle. We don't have a problem with that. We can make that happen. But I want to show you another trick. If I rewrite this first derivative like that, which is an equivalent form, 13 over that quantity squared is equal to 13 times that quantity to the negative 2, then I don't have to do quotient rule. I can do chain rule. As long as this is just a constant there, makes this work really nicely. Negative 26, x plus 3 to the negative 3 times 1. That's one version of the answer. Another possibility, though, and I want to show this to you because some of you would prefer, oops, what am I doing? Oh no, that's what I wanted to do. Some of you would rather just like do quotient rule again, which is fine. We could do that. X plus 3 squared times the derivative of 13 will be 0, minus 13 times 2 times x plus 3 to the first power times 1 over x plus 3 all to the 4th, because it's x plus 3 squared. This guy, big ol' mess, is 0, so check out what I'm getting here. Negative 26 x plus 3 over x plus 3 to the 4th that's the same as negative 26 over x plus 3 cubed, which is that exact answer I got using that chain rule trick. The quotient rule problem definitely is a little intimidating. We're good at quotient rule. We're not the greatest at simplifying all the time. But once we do a couple of these, and start to see sort of the pattern that happens. This particular scenario for quotient rule, getting my first derivative and then getting my second derivative isn't too bad. I'm going to save these notes and post them, and you can go back through the video again. At this point, you should go ahead and try the first 5 problems on the worksheet to see if you can go through the steps to find a first and second derivative for the functions that are there. Thank you.